This visualization represents the scale of the modern application layer. At layer 7 of the OSI model, alphanumeric identifiers are mapped to numerical network addresses billions of times a day to facilitate nearly all internet activity. Network engineers interact with this infrastructure through specific diagnostic tools. Executing the dig command forces the system to reveal the technical mechanics behind a standard hostname resolution. A successful response returns a no-error status code and a 32-bit IP address, providing the destination required for the device to route its traffic. To troubleshoot complex network failures, professionals must look past that final IP address and reverse engineer the metadata within this terminal output to understand the distributed hierarchy beneath it. In the early days of the ARPANET, this resolution was handled by a single centralized file called hosts.txt. This file, maintained at SRI International, contained every hostname to address mapping for every machine on the network. As the number of connected hosts grew, distributing this file to every node via FTP required a quadratic increase in bandwidth, creating a bottleneck that threatened the network's viability. This centralized model caused significant latency in address propagation. Because any change to a host address required a manual update at the source, name collisions became a frequent occurrence. In 1987, Paul Mockapetris formalized a solution through two primary request for comments documents. He codified RFC 1034 for high-level architecture and RFC 1035 for technical implementation. RFC 1034 established a system where no single entity would be required to maintain a consistent copy of the entire database. This transition to a decentralized hierarchical tree structure was driven by the technical necessity to scale the network beyond its original centralized constraints. Appending a trace flag to the dig command reveals the first operational hop in the resolution path, the Recursive Resolver. The Recursive Resolver serves as the primary interface between the end-user client and the global DNS infrastructure, handling the entire resolution process on the client's behalf. The resolver performs iterative queries, starting at one of the 13 root nameservers. Root servers don't store individual IP addresses. They provide a referral to a top-level domain server, like .com. Finally, the TLD refers to the Authoritative Nameserver, which returns the target IP. Authoritative servers hold the master zone file, synchronizing with secondary servers via zone transfers to ensure the domain remains resolvable during a failure. Dividing the workload between heavy client recursion and lightweight iterative referrals is the mechanism that allows the system to support billions of simultaneous queries. The answer section of the terminal output displays the fundamental data units of the system, resource records. The address, or A record, maps host names to IPv4 addresses, connecting you to web servers. A single domain can hold multiple A records, a configuration often used for basic load balancing. The quad A record performs the same function for the newer IPv6 protocol, utilizing a 128-bit address space for the growing number of devices. Every record includes a time to live, or TTL value, shown as an integer in the terminal output. The TTL acts as a local cache expiration counter. It tells the resolver exactly how many seconds it may consider the information valid before performing a fresh lookup. Managing these TTL values is a requirement for network engineers, as they dictate the propagation delay during server migrations and disaster recovery. Canonical name records, or CNAMEs, function as aliases that point one domain name to another, rather than directly to an IP address. Under strict protocol constraints, a CNAME record cannot coexist with any other record types for the exact same label. This restriction is critical when configuring mail exchange records, which identify the authoritative mail servers for a domain. MX records use a priority system for failover. A sending server will attempt delivery to the host with the lowest preference number first. If that server is unreachable, it attempts the next host in the priority list. Protocol mandates an MX record must point to a hostname with its own A or AAA record, not directly to an IP address or CNAME. Violating these record constraints is a frequent cause of network failures that can be difficult to diagnose without inspecting the raw DNS responses. The header section of the dig output contains metadata and status codes that describe the results of the query. A serve fail status often points to a breakdown in communication with upstream servers, while an NX domain response confirms that the domain name does not exist. The AA flag, which stands for Authoritative Answer, proves the response came directly from the master records and not from a cached copy. If the AA flag is missing, the answer was provided by a Recursive Resolver's cache. This reliance on caching raises a critical security question. If a response comes from a middleman's cache rather than the authoritative source, how does the system ensure the data hasn't been altered? Injecting fraudulent IP mappings into a resolver's cache is known as DNS cache poisoning. To succeed, an attacker must forge a response that matches the specific query ID, source port, and destination IP of the legitimate authoritative server. In 2008, the Kaminsky vulnerability exposed a critical network flaw. The attackers could query non-existent subdomains to bypass cache hits, forcing the resolver to repeatedly ask the authoritative server for answers. This created a race condition. The volume of junk queries provided attackers with thousands of attempts to guess the transaction ID and inject a forged record before the legitimate server could respond. If successful, the poisoned cache redirects all subsequent users to attacker-controlled infrastructure. DNS security extensions, or DNSSEC, mitigate this by digitally signing records, creating a hierarchical chain of trust that allows resolvers to validate data integrity. While DNSSEC ensures data authenticity, it does not encrypt the queries. Protocols like DNS over HTTPS and DNS over TLS encrypt the transport layer to provide query privacy. Because the original standards prioritized speed over security, modern networks must layer these verification protocols over the legacy plaintext architecture. This visualization represents the local scale of the system's infrastructure. The domain name system relies on a hierarchical delegation of authority and the pervasive use of caching to maintain performance across billions of devices. The integration of DNSSC, DOH, and DOT reflects a movement toward a more secure and private digital infrastructure. Managing this environment requires an operational understanding of record constraints, cache behaviors, and the metadata found in raw diagnostic output. Every command line query triggers a traversal of a decentralized database that has scaled from a few hundred nodes to the architecture that supports the modern internet.